عليكم السلام.
عليكم السلام دكتور، صباح النور.
Okay, we reach in tutorial 3 up to question maybe 3, I guess, right? Up to question 3. I'm going to go through the rest and then we'll move to the next section. Okay, so this tutorial is about the free vibration of rotational system, and you can have two types of a problem here. Either you have swinging motion or a rotational motion of a pivoted object, or you have this is the spring and the cylinder, or you have shaft. Okay, so here question number 4 is a shaft and a wheel. Okay, a steel shaft 50-inch long and 1.5 inch in diameter is used as a torsion spring for the wheels of a light automobile as shown below. Determine the natural frequency of the system if the weight of the wheel and tire assembly is 38 pounds and its radius of gyration about its axle is 9 inch. Discuss the difference in the natural frequency with the wheel locked and unlocked to the arm. And the moment of inertia, take the modulus of rigidity of the steel as 11.2 times 10 to the power 6 pound per inch squared. What we did in the section of torsion of shaft, this is the lecture, the one before. Okay, so this is the model we discussed in the lecture of, in the vibration of torsion of shaft. So that we have a shaft and it is carrying the disc, and we have here the center of the disc goes, the center line of the shaft go through the center of the disc. So it is omega n is square root of kt over j, which is j is the moment of inertia, and kt is obtained by the equivalent stiffness, which is pi gd to the power 4 over 32L. Okay, and then omega n, which is here in this example is shown. Omega n is square root of kt over jo. Okay, so the difference here in the problem we have, sorry, in the tutorial. Okay, this is the shaft is fixed here, and it is of length equal to 50 inches, and this is the diameter of the shaft equal to 1.5 inches, and then this is the center line of the shaft through the middle of the shaft, and this is the arm, and this is assumed a rigid arm and massless. Okay, this is the wheel of the automobile. Okay, so the arm is rigidly attached with the shaft, and the wheel has a mass equal to 38 pounds and has a radius of gyration if this is point CG, so that KCG, which is the radius of gyration, is given. Radius of gyration about its axis is 9 inches. Okay, so if you want to find the moment of inertia of the wheel, JCG is equal to M times, this is the weight, of course, not the mass. Okay, is M times KCG squared. Okay, this is the moment of inertia, and the mass equal to the value over G times KCG squared. Okay, this is the the center of gravity of the wheel does not lie on the axis of rotation, so we need to use parallel axis theorem. Now there are two cases here, not just one case. There is unlocked and unlocked cases of the wheel, you know, to the arm. If the wheel is locked, then this will be what we did in the theory about the shaft and the disc, but except that the wheel is shifted from the center of rotation. So you need to use parallel axis theorem. Okay, so there are, and if the wheel is unlocked, it means it becomes a point mass. Okay, so there are two cases, the unlocked. For locked, which means that you know, this is the point here, is either, if it is locked, it means that the wheel cannot rotate about the axle of rotation, about about this line. Okay, cannot rotate if it is locked. If it is, it can rotate with the arm. Okay, so let me just represent that. Here is the arm, and it's supporting. I can just add arm as this with length equal to 24 inches. Okay, and the shaft is providing stiffness, right? KT, where KT is obtained by pi GD to power 4 over 32 L. And here we have the wheel. The wheel, if it is locked, it means if the arm rotate about point, say O, it will have the center line. If I draw just a reference mark, okay, this line is the red in red is a reference mark. So if there is rotation about point O, the center line is coming to this position, and of course with the wheel. Okay, this is the wheel, and then this is the arm. If this is locked, the arm or the reference mark will also rotate. Right, so you can, this is locked because the wheel is rotating with the arm. And then the type of motion of the, you know, this is like rotating about a circle. Okay, it's like rotating about a circle. Okay, there should be contact point. So the type of motion of the wheel is general plane motion, translation and rotation. That means if you place a line on the wheel, you will see that line is rotating with the arm with the same amount of displacement theta. So the type of motion is translation and rotation for the wheel. And in that case, the arm and the wheel is, are one object. And that the moment of inertia Jo is obtained by parallax theorem JCG plus M times the distance squared. We say this is the distance is A. Okay, A is the distance between CG and O. Okay, I have to explain this for you because this is the maybe I think that you will, I need to explain it because there's something maybe new for you. Okay, so when the arm and the wheel are fixed, it means they are locked, they rotate together, and it means that the moment of inertia of the assembly, since the moment of inertia of the arm is 0, we have only the moment of inertia of the wheel. Okay, if both are, if the arm is not also the mass of the wheel, the arm is not neglected, then again, that the moment of inertia has to be counted for the arm, both of them, in the wheel and the arm. But here, the arm is assumed to be massless. Then we have only the moment of inertia of the wheel. So in general, we have JCG or JO is equal to J1 plus J2 for the arm and for the wheel. Okay, since the moment of inertia of the arm is 0, then this will be only of the wheel. So JO equal to the moment of inertia of the wheel. The moment of inertia of the wheel is obtained by the parallax theorem, JCG plus MA squared. The A is the distance from O to center of gravity. Okay, and then that's it. JCG is the M times KCG squared, and K is given 9 inches, and the weight is given. Then we have to use W over G, and everything in inches. Then G is 386. Okay, and that will give you omega n, square root, or if you want Fn, I think the answer is given in hertz. Okay, so you use Fn. For the unlocked, if I do the same thing, I will draw the center line, and here is the wheel, and we have the arm. Okay, and the shaft is on the torsional, is representing a torsional spring. Okay, so this is point O again, and this is point CG, and here is the distance A. Okay, again, we put the reference mark on the wheel, and we draw the second position. Okay, here is the wheel, Okay, here is the arm. The reference mark will be still horizontal. This is for the unlocked. The unlocked, it means that the wheel can rotate about the axle point, the axle of the wheel, which is like the pin connection. So it can rotate. The wheel can rotate about the pin point, about the pivot point, which is, we call it the axle. So there is no rotation here. So the wheel becomes a point mass. No rotation, right? So it's only translating. So that this reference mark is always horizontal, because I already put the reference mark horizontal. And in this case, JCG for the wheel is equal to 0, because this is the moment of inertia of rotation, which it is not rotating about the center of gravity. So no rotation, it means that JCG equal to 0. And then JO, using the parallax theorem, is JCG plus M times A square. This part is 0, so it is MA square only. Okay, and M is W over G times A square, and A is 24 inches. Okay, so the same thing here. This is equal to JCG plus W over G times A squared. Okay, so this is the difference between locked and unlocked. That for locked, there will be rotation as well as a translation, but for unlocked, it is only translating, curvilinear translation, but there is no rotation about the center of gravity. And then that moment of inertia about center of gravity is 0, and we take this as a point mass. Okay, it is like hanging a mass with a cord. Okay, this is a cord, and this is like okay, so it is only moving up and down. Okay, so it's become a point mass. Or if just put a mass here, and this is point mass. And then omega n becomes the same equation, of course, but we will have J is different, or if n equal to 1 over 2 pi square root of kt over m over J, I mean, okay, Jo. So kt is the same, but Jo is different for locked and unlocked. Okay, question number 5. If you have no questions. A simple pendulum consists of a bulb of mass m suspended on a massless bar of length L. Derive the differential equation for the angular displacement theta of t of the pendulum. Linearize the equation and find the natural frequency of a small vibration. The reason I put the question here and ask you for derivation using AR and A theta is just to recall what you did in dynamics. You can introduce, this is the simple pendulum, and it is called simple because the mass is above mass, okay, which is point mass. Okay, for point mass, JCG is 0 always for point mass. And the chord is massless, so we have the mass is only the mass of the bulb mass. And this is the radial direction. R is the radial. And this is called the transverse. And the transverse is perpendicular to the radial. The direction of the radial is outward from the point of rotation. And this is the also you can take this in this direction positive. Theta is the angle the pendulum makes with the vertical center line, which is the equilibrium position. If you put, there are two different ways of solving this equation. You can use sum of forces in the r direction and theta direction, and then find the question is to find the nature frequency for small oscillations. It would be a nonlinear equation, and you can linearize it. Okay, the free body diagram of the mass, when you draw the free body diagram of the mass, it means its weight, which is equal to mg, and the tension, T, in the chord. And then you resolve forces. We have expression for AR and A theta. Now, what is R here? R in this problem for a mass attached at a distance L. So this is R, L equal to R, equal to constant for the pendulum. So what is R that become equal
Zero.
to R double, equal to R double that equal to 0. Exactly. Okay, because R is constant and R equal to L. Then sum of forces in the theta direction, this is theta, and the theta direction is the transverse. It means you resolve along theta direction. Okay, the forces we have is minus W sine theta, and equal to MAR, right? And let me write this. That equal to MAR. So sum of forces we have is minus W sine theta equal to M, and AR is R double that which is 0 minus R which is L times
دكتور مو A theta.
A theta, yes, exactly. Which is R theta double that which is L theta double that plus 0, because R that is 0. Okay, and W is mg, so it is minus mg sine theta equal to ml theta double that. So as you can see that L and L can, there is no, sorry, that M and M cancel out, and then you have, and you can divide by L. So this becomes theta double that plus G over L sine theta equal to 0, which is the nonlinear differential equation because of sine. Okay, this is sine. And you can approximate, linearize this by using for theta very much less than 1, we have sine theta equal to theta, and this equation becomes theta that plus G over L theta equal to 0, which is the linear equation, and the second order ordinary differential equation, and therefore omega n is the coefficient of theta, is omega n square, and omega n becomes square root of G over L. Okay, if you want to use sum of forces in R direction, you can find the tension. Okay, but there is no question about the tension. Okay, this is one approach. And the second approach is we take the moment about point O. Okay, take sum of moment about O equal to JO theta double dot, which is the Newton's second law and rotation. Sum of moment about O, the tension is not doing moment about point O. It is only the weight. Okay, so the weight, you draw the complete the right angle triangle. This is the perpendicular distance, which is L sine theta. So the moment of W is minus because it is clockwise and theta is counterclockwise. So it is minus W times L sine theta. L sine theta is the perpendicular distance, which is part of the right angle triangle here, which is the opposite side of to theta, equal to JO. For Bob mass, use parallel axis theorem. What is JO? JO is JCG plus M times the distance square, which is L. And since JCG is 0 for the Bob mass, this becomes only ML squared. Theta double dot. Okay? And when you simplify, there's one L will cancel out with L, and M will give you here G. Then the equation becomes divided by L becomes theta double dot plus G over L sine theta equal to 0, which is the same equation we obtained with the first approach. Simplifying or linearizing, we get theta double dot plus G over L theta equal to 0, and then omega n equal to square root of G over L. Okay, but if this is not above mass, it is like if it is a disk rotating, and it means that we have, instead of cord, you have maybe a rod. You can assume the rod to be massless, so it will not bend. And that the moment of inertia depends on the wheel or the disk attached is locked or unlocked. Okay, so just something came to my mind that if you have a rod and it carries a wheel or a disc, and it is, if you assume this is massless rod, then you have the moment of inertia of the disk only. Okay, this is not above mass, it is a disk. Then the moment of inertia about point O, if this is pivoted here, let's see. Okay, this is point O, it is rotating about O. This is point, let's say A. It depends, the moment of inertia of the disk about O depends on how the disk is fixed with the rod or the arm, as we did with the question of the wheel and the arm. So if it is locked or it is unlocked, the equation will be different. Okay, question 7. A heavy ring of mass moment of inertia 1 kilogram meter square, which is J, is attached at the end of a 2-layer hollow shaft of length 2 meter. If the 2 layers of the shaft are made of steel and brass, determine the natural time period of torsional vibration of the heavy ring. And the loss of rigidity of the steel is 80 gigapascal. and for the brass is 40 gigapascal. So this is exactly same as what we did in the class of the torsion of shaft here, except that the shaft is hollow. Okay, so it is omega n or tau n required is equal to 2 pi square root of j over kt. Okay, j is given is 1. This is j. And kt is pi g d to power 4 over 32L for solid shaft. For hollow, the two layers, hollow shafts we have. There are two shafts as you can see, not one inside the other one. So you need to find the stiffness, and those are, let's say, welded together. So they have the same angle of a twist. And if they have the same angle of a twist, it means that they are in parallel. So KT becomes KT of the brass plus KT of steel. Okay, so in general, KT is pi g d to power 4 over 32L, and KB is hollow with inner diameter equal to the brass is the one inside the steel. So the inner diameter is 3 centimeter, and the outer diameter is 4. Okay, and for the steel, we have the D inner is 4 and D outer is 5. So the outer diameter for the brass is the inner diameter for the steel. So that's it. You have, instead of D to power 4, you will have between parentheses D outer to power 4 minus D inner to power 4. And they have the same L, that L equal to 2 meter. Okay, and then you add them in as in parallel. So it is KB plus KS. Okay, so KB is equal to pi G for the brass, T outer to power 4 minus D inner to power 4 divided by 32L. Okay, let me just change this to capital D. And for steel, it is pi G of steel, D outer to power 4 minus D inner to power 4 divided by 32L. And use the base units, 80 gigapascal converted to Newton per meter, and also the diameter converted to meter. Instead of centimeter, you use meter. And the question number 7 is similar to question number 6. I don't think you will have a problem. Is that a steel shaft of 0.05 meter in diameter and 2 meter length is fixed at one end and carries at the other end a steel disc of 1 meter diameter and 0.1 meter thickness. So we have information about the shaft, and it is steel, which is the material, the diameter, and the length. Of the disc, we have dimensions and steel material. So it is steel, and it has a thickness, okay, equal to 0.1 and a diameter of 1 meter. Okay, and this is made of steel. Find the mass of the disk and its moment of inertia. Mass of the disk is from the volume and the density. So M equal to rho times V. And you find rho for steel. Okay, volume is the volume of the shape of the disk, which is a cylinder. And the moment of inertia about CG is equal to 1 over 2 mr squared for a disk. And part B, the stiffness of the steel, which is pi g d to the power 4 over 32L. Then the system nature frequency. I think this will be straightforward. And the question number 8, a horizontal platform P is held by several rigid bars, which are connected by a vertical wire. Okay, so this is the plate. And those are rigid bars. We have 4. And then this is the wire. The wire. The period of oscillation of the platform is found to be 2.2 seconds when the platform is empty. Empty, it means without object A. Okay, you have only the platform. And 3.8 seconds when an object A of uniform moment of inertia is placed on the platform with its mass center directly above the center of the plate, knowing that the wire has a torsional constant K equal to 27 Newton meter per radian. Determine the moment of inertia of the object A. So there are two systems here. Stiffness is coming from the wire. Okay, so it is KT, which is given as K equal to 27. The plate has a moment of inertia Jp, but we need to calculate Jp, and A is also has a moment of inertia Ja that is unknown. And there are two systems here. The first system is the empty platform. There is only Ja here. And the other one is when the platform and the object. Okay, and the object. The center point of the object A lies on the center point of the plate. So if you draw the diagram, okay, they enter the center point of the plate and the center point, or the center of gravity of the plate is the same, and the center of gravity of the object, they coincide. Okay, so if you take a side view, you will see that this is the plate and this is the object. Okay, those both are the center of gravity lies on the center of gravity of the platform. So what is how do we use this information? It means that J is equal to J of the plate plus J of the object. Okay, the way the object is added on the plate, it means that the moment of inertia is to be simply added. It's like adding mass over mass. But here we have the moment of inertia are added. It depends on the if we need to use Parallax's theorem or not. Okay, so suppose we have a plate is here and the object is placed here. Then this is center line of rotation, and this is the center of the center of rotation is passing through the center of gravity of the plate, and the center of gravity of the object is shifted. Then this is A has Ja about this line has to be obtained by Parallax's theorem. in order to find the moment of inertia. Okay, so this has JACG. We have to bring moment of inertia of JA about point O, let's say. Then about point O is obtained by Parallex's theorem. MA, and this distance is D. And this has a moment of inertia JP. Then the total moment of inertia about O is JP plus JA. But JA is obtained by Parallex's theorem. Here we don't have Parallex's theorem, just JA and J plus JP. Okay, JA, first of all, we need to find JP because the period of oscillation is we have is when the plate is empty, then tau equal to 2 pi square root of J over KT over K. Okay, and J is of the plate. The only unknown here is JP. So you can find JP, right? And for the second system, we have, this is tau 1. Tau 2 is the same thing. This is the same. The system is similar, but the moment of inertia is different. It's square root of JP plus JA divided by K. And then from here you can find JA, the required quantity. Okay, any questions? Okay, in lecture 8, I don't think I will be able to finish, but I will just start. Rayleigh method, this is the new section. It's about finding the effective mass. We find equivalent stiffness, right, of some object like the rod or a spring or a beam, cantilever, simply supported, or fixed beam. Here, this is related to the mass. As you know that the mass of the spring is, so far we assume it is neglected, and also the mass of beams, when they act like a spring, also their masses were neglected. Some of the example we did, like the water tank and the column, we neglected the mass of the column, and all the problems we did about cantilever beam or fixed beam, that the masses of the beams were neglected, and that is an assumption when the mass they carry is heavy compared with their mass. The mass of M is very much greater than the mass of the spring. The corrected equation, or the more correct equation is for the nature frequency is when you consider the mass of such elements. There are the systems can be classified as two types of systems here, either as discrete, or continuous system. The discrete is when you have the masses are the lumped masses. For example, if you have a mass M1 and then you put a mass M2 on top of it, then what is the M effective? It is the M total. It is M1 plus M2. Okay, but if you have a rigid link and pivoted, you remember one of the examples were something like that. Okay, This is a rigid link. So what is the number of coordinates here? For rigid link, okay, rotating about point O, then this is called single degree of freedom because there is only one coordinate required, which is theta. But if you place a mass, let's say we put a mass here. This has a moment of inertia JO, and this has a mass M. This is if this is rigidly attached with the bar, the mass is rigidly attached with the bar. We have still single degree of freedom system, and then we have to find M effective or J effective. But if you find M effective, it means you are finding an equivalent system as spring and M effective with K effective. Or if you find J effective, it means you are finding a shaft, okay, just a disk, I mean, and pivoted and with a torsional stiffness. So this has J effective, and this has K effective, but in torsion. Okay, this is KT. So either this, either torsional, either translational system, or rotational system. Those masses, the mass of the bar is at CG. Okay, so this is M. Let's say M1 times G. This is M2. So those are called discrete. This is not flexible. Huh? If it is flexible, then it is something else. This is rigid. Then the mass is at the center of gravity, and also all the points on the rigid bar are related. Yani, if you take the just 1 minute, huh? If you take the bar and rotate it, if this bar is in rotation about this point O, it means it will take a different position. Let me just draw it. Okay, this is the same thing, but it is rotating. So all the points are related together because this will stay straight. Okay, if this is straight, this will stay also straight. So the points, let's say if you want to compare point A and point B, what is the, this is point A and this is point B. You can have a right angle or similar triangles, right? This is a triangle, and this is another triangle. Those are similar triangles. So the motion of point here B is related to point A. I mean, if you put, this is rigid. So if you put a mass on this point, let's say M2 or MA, and this is MB, this is point B, and you put a mass here, those masses are related. their motion are related because of the similar triangles, all in terms of theta. Theta here and here are the same because this is the similar triangles. So XB and XA can be obtained in terms of theta. And this happens if you have rigid bodies. The same thing if you have gear in mesh. This is gear A and this is gear B. This has a moment of inertia JA and this has a moment of inertia JB. This can be given as or represented as one object in rotation. If you have a a shaft here, then this can be the shaft, and then this will be just J effective. And instead of JA and JB, you have J effective. Here you can have also J effective or M effective if you find in terms of XA or XB. Okay, so we'll come back to this section next time, inshallah. We will take some examples and hopefully we'll understand it more. Any questions? Okay, see you, inshallah. Regarding the quiz, it will be on Tuesday at 6:30 about tutorial 2.
دكتور هالاسبوع ان شاء الله بيرجع الدوام
يوم الخميس. قالوا الخميس، بس عاد ما احنا عارفين الموضوع الحين. نشوف شو يصير، لان مخلينا اختياري، يعني اللي بيحضر واللي ما بيحضر، فاحنا ما أدري. انا لحد الان ما ادري شلون بيكون الوضع، لان معظم المواد اللي يدرسهم دكتور واحد، يعني مثل الحين هاي المادة بس انا ادرسها، فشلون بقسم نفسي يعني حق اونلاين وحق الحضور؟ اوكي، الا اذا الجامعة بتسوي البث مباشرة، يعني هم يوجدون طريقة من الصف يسوون بث للي اونلاين. اوكي، ما احتمال يكون في اجتماعات الايام دي ونعرف الموضوع.
Doctor?
Yeah.
When is our first quiz? Our first quiz.
First quiz, and here first quiz is this week on Tuesday.
Oh, thank you.
Yeah, about tutorial 2.
Okay, doctor. Thank you.
مع السلامة.